Thanks.
That's the next slide. This is the previous slide.
All right, good morning. I'm Jim Dinan from Intel. I lead our OpenSHMEM team, and I also serve on the OpenSHMEM specification committee. So what I wanted to share with you this morning is some of the things that are happening with OpenSHMEM. There have been a lot of changes recently, and also some of the things that we're doing within our team to implement all these new features in OpenSHMEM. And I'd like to also acknowledge Dave and Kayla, who've done a lot of the great work that I'll present this morning. So before getting into the details, I thought I ought to at least introduce a little bit what is OpenSHMEM for anybody who maybe hasn't seen it before. If you're familiar with MPI, this will look pretty similar. OpenSHMEM is a communication library that's used by HPC applications. It is a member of the Partition Global Address Space family, and it utilizes an SPMD execution model, so similar to MPI. So in the picture here, we're running 4 SHMEM processes. In the SHMEM terminology, SHMEM calls these PEs, processing elements, just to be different, but they're the same sort of thing as MPI processes. Each process gets some integer number that's assigned to it, which is how we distinguish individual processes. As I mentioned, SHMEM is a partition global address space model, so instead of having just private memory within a process, each process also has some memory that's remotely accessible. And in SHMEM, there are 2 segments. The first segment is the symmetric data segment, and this is literally the data segment from your binary. So all of the statically allocated data by the application is remotely accessible. And the second segment is a symmetric heap, which is used for dynamic allocations. And the way that you access this memory is through OpenSHMEM library calls to do reads, which are called get operations, write, which are puts, and atomic update operations. And so from the perspective of an individual process, in our 4-process job here, this is all of the data that can be accessed. And we refer to the aggregation of these remotely accessible segments as the partition global address space. So each piece of this data has some locality information associated with it, which is where the partitioning comes from. And this process can do gets, puts, and atomics to access this information. By default, all the operations performed by OpenSHMEM are unordered. So this is something that's different from MPI sends and receives, for instance. When you want to get ordering, the application performs an operation called fence. And what the fence ensures is that everything the process did before the fence occurs or is visible before things that are done after the fence. You have a quiet operation, which gives you remote completion for all of the posted operations. And we also have ways to synchronize the individual processes by using barriers or by waiting for data to show up in locations in memory. And those waits are done through the OpenSHMEM interfaces so we can make them portable. SHMEM itself has been around for nearly as long as MPI. I think SHMEM was first introduced in 1994 by Cray. Since then, SHMEM has been supported by multiple different vendors on different types of systems. And so what sort of happened in that environment is that there were a number of inconsistencies between the different implementations. And so the user community got together several years ago, and they convinced SGI to allow the community to make an open specification for SHMEM. And the advantages of this are really twofold. The first is that the users get consistent behavior across SHMEM libraries. And the second is that it gives the user community a way of introducing new features into SHMEM through an open standardization process. So last December, the OpenSHMEM committee ratified OpenSHMEM 1.4. This was a pretty big change in OpenSHMEM. There were a lot of new features that were introduced. There are 2 that I'll focus on in today's talk, thread safety and our communication management API, which we have given the not overloaded name contexts. So I'll try to say OpenSHMEM context, and that's what I mean. And these really introduce a pretty unique threading model, which I think sort of works its way down through the networking stack in kind of interesting ways. It allows the middleware to actually identify individual threads and gives us new opportunities to do optimizations that we didn't have before. There are a number of other routines that have been introduced for inter-process synchronization, for managing data in the symmetric heap. Bitwise atomic operations were introduced in OpenSHMEM 1.4. And something that's pretty neat, just as far as the mechanics of the API go, is that the OpenSHMEM community has been pretty active about adopting C11 generic interfaces for the APIs, which is kind of neat. We're actively working on OpenSHMEM 1.5, and we are looking at a lot of the things that have been mentioned at the workshop. We're thinking about how do we account for persistent memory in the OpenSHMEM interfaces? Does a quiet guarantee persistence? Do we want a different operation for that? How do we account for multiple different memory kinds within a given system? How do we deal with multi-rail? All these different kinds of things. We're starting to try and account for these in the OpenSHMEM interfaces. And so we would be happy to have any and all of you come and join OpenSHMEM.org. It's an open group, so feel free to check it out if you're interested. As I mentioned, we're also engaged in implementing OpenSHMEM in open source. We've been doing this through an open source project called Sandia OpenSHMEM. This formerly was PortalSHMEM. We've since expanded it and renamed it since it now includes OFI support. We have a release candidate out with support for the new 1.4 spec. This is out on GitHub and open source. And we were the first open source implementation to support both OpenSHMEM 1.3 and OpenSHMEM 1.4. So by extension, OFI was the first communication stack to support both of these new OpenSHMEM standards, which I think is pretty great. If you're interested in trying Sandia OpenSHMEM, which we shortened to SOS, if you're interested in trying SOS, what we require out of a provider is RMA, atomics, and reliable datagrams. And for pretty much all of the other features, we can work with whatever's available in the provider. The thread safety API in OpenSHMEM looks pretty familiar if you've seen MPI's thread safety interface. When you initialize a library, you can choose the level of threading support that you're interested in. And we have single, funneled, serialized, and multiple. Essentially, single means there's no threads. Funneled and serialized are different levels of serialization guaranteed by the application. And then multiple is all the threads are making OpenSHMEM calls. And in terms of what we utilize from the libfabric layer, we can work with providers that support both FI thread safe and FI thread completion. And so I'll talk a little bit more about how these kind of play inside the implementation. But what's nice about FI thread safe is that we don't have any mutexes at all in our middleware. It's the synchronization is handled entirely in the provider, and the provider can do the synchronization intelligently on our behalf. When we use FI thread completion, we end up needing to introduce mutexes at the middleware level. So there's no synchronization that's required out of the provider. Synchronization comes up to the middleware. But because of the way that the communication interfaces are specified in SHMEM, we're actually able to eliminate these mutexes entirely. The next piece of threading in OpenSHMEM is a feature that we call OpenSHMEM contexts. And so before I show you the API, I thought I would just sort of show you pictorially, like in a cartoon, how this works. The picture on the left-hand side shows an OpenSHMEM job where we have a SHMEM process that's got two threads, and it doesn't have contexts available. So both of these threads are injecting their communication operations. These are, each of these represents a put. They're injecting their communication operations, but they effectively go into the same channel. So when either of the threads performs a quiet to ask for remote completion, all of the traffic generated by that process is impacted by the quiet. So we see that these threads are interacting with each other. What contexts allow us to do is to create multiple of these channels. And so what we see is each of these threads has its own channels. So this quiet over here, performed by the lower thread, doesn't affect the communication that's being performed by the upper thread. And in addition, this thread or even a process in a non-multi-threaded SHMEM job can have multiple contexts, which allows it to separate communications that it's performing and have control over overlap between different communication operations. So this is what the interface allows us to do. Here's what the interface looks like. We have creation and destruction operations for contexts. And then the real place where they appear in the API is we've introduced new versions of all the communication routines in SHMEM. And these communication routines take this context as an argument. So the channel in which the communication is performed is now an argument to each of the communication routines. And the ordering operation and the remote completion operation, the fence and quiet operations, these also take a context. So you're able to selectively influence individual channels of communication that are happening. And within these contexts, the communication is unordered. And also across contexts, it's unordered. You may have noticed that the context creation operation has an options field. This options field is what enables us to eliminate synchronization. The user can tell us about their usage model through the options field. So the user can tell us that the usage of this context is serialized. So in a multi-threaded job, the user can tell us that the context is used by multiple threads, but don't worry about it, I'm going to take care of any serialization that's needed. So only one thread uses this at a time. They can also provide a stronger guarantee, which says that only the thread that created this context will ever use it. And so when the user gives us these guarantees, we're able to actually eliminate the synchronizations that we're doing inside the library. I apologize the text is so small. I have just a quick code example to kind of show you in a little more detail how the API works. What this example does is it does a simple dynamic load balancing. So we have a process. So each process has some threads inside of it, and it has some number of tasks that are assigned. So all the processes have some number of tasks, and the processes themselves are multi-threaded. What you do first is you process all of your local tasks, and then you go to the next process, and you process their tasks, and so on. So there's this kind of dynamic load balancing that's happening, consuming the tasks across all the processes round robin. And so you do your local work first, and then you help all of the other processes. And the way that we do this load balancing in this example, and by the way, this example is also published in the OpenSHMEM spec, so you can see the complete code for it there. The way that we do the load balancing is there is a task counter, which is the top line here, which is in the symmetric data segment. And we do a fetch increment on this task counter to get the next task. So I start first with my task counter, and then I go on to the next process's task counter, and so on. And the fetch increment operation, because it's a fetching atomic, we need to wait for it to complete. And the way that we handle completions in OpenSHMEM is we use event counters. If multiple threads are using the same event counter, it's not possible for us to distinguish their operations from each other. So we end up having to wait for this event counter to quiesce in order to know that our fetch increment operation completed. So there's a lot of interference that you get between threads in sort of the baseline way that you could implement this. So we introduce context to allow each of the threads to have a separate channel for performing their fetch increments, which effectively gives each thread a separate completion counter and eliminates that interference. So we have an OpenMP parallel region here, and then you can see this is the load balancing loop, where first we start with RPE, and then we do this fetch atomic, and we just continue processing fetch atomics on the same PE until we've sort of exhausted that counter and go to the next, and so on. So that's the way the API kind of functions in a quick example. Now I'm going to transition from talking about how the API works to telling you about how we implement it using libfabric. So I tried to come up with a sort of brief picture which pictorially shows you the relationship between the different libfabric objects that we use in our OpenSHMEM implementation. Starting at the bottom, we have the fabric domain. And on the fabric domain, we register the heap and data memory regions. Alternatively, if we know that the address space layouts are the same, we can do this with a single registration, which helps to reduce the number of instructions on our critical paths. So that's a performance optimization that's available for users to enable. So we've registered the memory down here on the domain. Now we need to expose it for remote access. And we do that by creating an endpoint over here that I've labeled the RX endpoint. And we don't transmit anything on this endpoint. It's just for enabling access to the memory regions that we've registered on the domain. The address of this endpoint gets registered into the address vector at every process so that we can use it when we're performing communication operations. I think one of the things that we're thinking about as we continue to sort of tune and evolve our implementation is how many of these RX endpoints we need in order to support things like multi-rail, or in order to make sure we're taking full advantage of the capabilities of the individual networks. We have an optional feature on the RX endpoint to stick an RX counter there, which we can use to optimize SHMEM wait operations in single-threaded mode. Not all providers are able to support this efficiently, so that's an option that can be disabled if the provider prefers that we not use it. And then what I've shown here in these dashed boxes are two OpenSHMEM contexts. The one in the center is the default context. So the way we maintain parity with the legacy SHMEM API is we say there's this SHMEM context default object, and if you're using the legacy OpenSHMEM 1.3 API, where the communication operations don't take a context argument, we say that's equivalent to calling the new API with this SHMEM context default. So that's what's in the center here is our SHMEM context default. We see that this has some additional features that are not enabled by default on all of the contexts. In particular, we have an endpoint over here that we use for buffered puts. And we use this to bounce buffer blocking put operations, which converts the blocking puts into non-blocking puts. Up until OpenSHMEM 1.2, we didn't have non-blocking puts in OpenSHMEM, so this was a useful optimization. And we still support it for those existing codes. But since we expect this to be most useful for older codes, we don't enable this by default on the context API, since if you're using the new API, we expect you're going to use some of the other new features too. In order to support this, we have a completion queue where we capture full events so we can reclaim bounce buffers. All of the other operations are issued on this counter endpoint, which uses event counters to capture completions for the individual puts and gets that are performed. And we have separate counters for puts and non-fetching AMOs versus gets and fetching AMOs, since they get treated a little bit differently in fence and quiet operations. It allows us to optimize our blocking behaviors. That's the default context. We've got another context over here that the user has created. And we see that it's essentially just this counter endpoint. And if users want to, they can give an option to enable bounce buffering on their endpoint. We use STXs as our transmit resource. And so what the library does is it maintains a set of STXs that have been allocated and assigns those to contexts when they're created by the user. So we can see is that the user-created context has one STX, and the default context over here uses the same STX for both of the endpoints. So let me show you a little bit what this looks like when the usage model gets multi-threaded. This is showing an example. So I've taken away a lot of the objects that aren't as relevant here. This is showing an example where there are 3 threads. Each thread has created 2 OpenSHMEM contexts. And in addition, the user has told us that these are private contexts. So we know that these 2 contexts belong to the same thread, and these 2 belong to the same thread, and so on. And so what we're able to do inside the implementation, since we know that both those contexts belong to the same thread, we map them to the same STX. We effectively privatize an STX to a thread and take on that sort of resource management at the middleware layer. So one of the questions that we have gotten several times is, well, why don't we use scalable endpoints? And I think this picture sort of helps to capture that pretty well. We could use scalable endpoints, but we lose the opportunity to manage the STXs here. And so we effectively lose that opportunity to take advantage of the hints the user gave us about the multi-threaded usage model that their application is using. Since we are taking on the job of managing these STXs in the middleware layer, we have to have, we implement some policies to manage this resource. And we call it our STX allocator. And it controls the assignment of STXs to contexts. By default, a context is shareable, which means that it can be used by any of the threads at a process. And the user is able to sort of restrict that usage model by giving us some of these options. What we're showing in green here is the default context. And this is shareable. And we allocate it during initialization. And that gets mapped to our first STX. So we're over here is sort of a cartoon of an HFI. And then we've shown these little circles inside the HFI. And these are the resource that an STX corresponds to that we're sort of managing through these OFI STX objects. And on each one of these, we have a reference count, which tells us how many OpenSHMEM contexts we've allocated it to. So the first thing we do is we create this default context. We stick it on the 0th STX, and we increment the ref count on that STX. When the user creates private contexts, we capture the ID of the thread that performed that creation call. So when a private context is created, we know that the thread creating it is the only thread that's ever going to touch those resources. So we use the Linux get_tid system call to query the thread ID for the calling thread, and we capture an association in a thread to STX mapping table. And so what we're showing here is the individual thread IDs mapped to STXs. So each of these threads has performed a private context allocation, and we've privatized an STX to that thread. So when the application creates a private context, we're going to check this table. And that's what we're showing here. This in our picture here is thread 5 is creating a private context. We look in the table, and we see that thread 5 has been allocated STX4. So we're going to go ahead and bind the endpoints corresponding to that private context to the 4th STX. And similarly, for shared contexts, we have to manage resources too. So you can imagine that over time, we have a mix of private and shared context. And there are various strategies that you can use to try and accommodate the usage model of the application and map it efficiently to the resources that we have available. So we have random allocation policies, round robin, least use, different things like that. And what we've seen is that the best allocation policy really will be derived by the application's usage model. In addition, we can have multiple SHMEM processes running on a node. And we have they effectively have to share the transmit resources provided by the HFI. So we have different strategies for partitioning those resources. We can do an auto partitioning by figuring out how many processes are on the node and asking OFI how many STXs we have available, and so on. And so hopefully what I've conveyed is that we have this new threading and communication management model that has been adopted into OpenSHMEM, and it introduces some new and interesting opportunities for us to optimize multi-threaded communication. And we're able to do that pretty effectively using the interfaces that we have through libfabric. So just to show you really quick a couple performance results. These are pretty early results. These are taken using the Sandia OpenSHMEM 141 release candidate. So this is still sort of work in progress, but we wanted to show what we're seeing. This is a multi-threaded point-to-point unidirectional bandwidth test. So we've got 2 SHMEM processes on different nodes. Both the processes are multi-threaded, and we're doing a bandwidth test from one to the other. And so what we see is the bottom line down here is where we've got 1 thread in each process. And then the green line, the next one up, is where we have 2 threads and then 4 threads. So we see what we're seeing is that as we add threads, we're actually able to increase the throughput that we're seeing, which is great. This is exactly what you want to see out of a multi-threaded communication library. This might be a little bit difficult to see from the back of the room. Hopefully you can follow along on your own screen. But the next thing that we started looking at is if we change the policy that we use for assigning STXs, how does this influence performance? So what we've done is we have the same test again, one process on each node, but we've fixed the number of threads at 8. And we're just changing the number of STXs that we allocate to each of those processes. And so on the left-hand side, the STXs are being privatized. So in this test, each thread has a context, and it informs us that the context is private. So basically, we take advantage of this information on the left-hand side to privatize STXs. And on the right-hand side, we disable privatization so that the resources stay shared. And so on the left-hand side, what we see is we see a continuous improvement as we increase the number of STXs up until we've got a number that's equal to the number of threads in the benchmark. On the right-hand side, what we see is that there's actually some benefit from sharing if the number of STXs that you have is less than the number of threads that are running in the application. And so that's what you see here. Down here at the bottom is sort of our baseline where we've got one STX. And then crowded together here are the 2 through 8 STX lines, where we still get some increasing benefit from adding STXs. But if we have a number of STXs that's less than the number of threads, we actually get we get the most benefit, at least for this particular application, by maintaining those as shared rather than privatizing them. So what we're observing here is that there's more work for us to do sort of in terms of understanding the usage models and coming up with the right optimizations to get the best performance out of the usage model that's exhibited by the application. So that's it. I'd be happy to take any questions. All right. Thank you.